Okay, guys. So your test review was the assignment that we did in class today, which was kind of like um, a breakout room type deal. You had problems that were at different cards and different levels, and you had to answer them correctly in order to move on to the second level, third level, four, and so on. Winning team, got points extra credit towards the test. Losing team didn't. So if you weren't here, okay, this is basically what happened. There was a picture in level one. You had some QVC codes you had to do. It sent you to these sites. You had to answer them, and when you did, it came. If you got it right, you got a letter. So like the first one, they said, okay, you're moving something a distance of 40 meters in 10 seconds, and you use, it requires 9,000 joules of work, but they asked for the force. So one of the equations that you have for force is work over distance. So the 9,000 joules over 40. We didn't need time here. It was in the problem, but we didn't actually need it. You got this, and it told you letter S. Here, it gave you force, mass, and distance. It wanted work, so you only need force and distance. You didn't need the mass in that case. And you get 750 joules. It gave you the letter P. Here, you're given power and time. They want work. Work is equal to power times time. Multiply, you get an answer, get a new letter. And the last one, all right, they want you to solve for power. Work over time, 12,000 over 8, 1,500 newtons. Okay, and then you had to rearrange these into a certain letter, or into a certain word, and the word was push. Once you got that complete, you were able to get onto level 2. One of the questions here, level 2 was, a hamster can do 50 joules of work in 5 seconds. How many hamsters would be needed to power a 60-watt light bulb? Well, let's say power is equal to work over time. All right, one hamster can do 50 joules of work in 5 seconds. Divide out. So 10 watts per hamster. If you needed 60 watts, you would need 6 hamsters. So the answer to A was the number 6. That's one of the things. That's one of the numbers you needed for the next code. Then in part B. In part B, you had kinetic energy of something. Well, the problem was you were given it in grams. You have to divide out by 1,000 to put it into kilograms, and then use the kinetic energy equation of 1/2 mv squared. By doing this, you get an answer of 8 joules. 8 joules. Then, because you were given already there the velocity 16, and then the last one, or for part C, this is the one that seems to give people a lot of problems. All right, well, with this, you had a banana, 2 kilograms, and it's dropped from this much of a height. They want to know what the velocity is when it hits the ground. So what you're given is mass and height. So basically, think about it from a table. All right, velocity at the top would be 0. Therefore, kinetic energy would be 0. So at the very top, all of your energy is potential. Mass times gravity times height, 1 times this times 10 or 9.8, whatever you get. That's all of your potential energy. You have to know that mechanical energy for a closed isolated system is kinetic plus potential. So with that, right, this dude plus this dude is going to equal your mechanical energy. So 0 plus that 2.5 is this. Mechanical energy is 2.5. So that's telling us at any given point, whether it's here, okay, kinetic energy and potential energy have to add up to be that number. Well, they wanted to know what it was as it strikes the ground. Well, as it strikes the ground, the height you have to know is 0, which means mgh, anything times 0, is 0. So at the bottom, if the potential is 0, the kinetic energy has to be 2.5. Why? Well, remember, mechanical energy at every single point has to be that 2.5 itself. So, 0 plus blank has got to equal 2.5. Kinetic energy has to be itself 2.5. And once you know that is your kinetic energy, you use this equation to solve for V. 2 times the kinetic energy divided by the mass, and this is supposed to be 0.2. There was it was a pain in the butt to write by accident. Accident messed up, so 0.2. Get square root of 25, 5 meters per second. So then you would have used that code of 685 in order to get onto the next level. So also on the back of 2, you had like pieces of a QVC code, which you needed for later. Plus in part 1, you had these little people. You had these people, which you would need for the later part. And also in part 1, those QVC codes that we used to get to there was something on the back that says rank the missing energies in order and add up the corners, or count the corners or sides, whatever. So that's a clue for one of the next things. That's one of the clues for the next things that we will be doing. So we go on to number 3, part 3. You have these kinds of problems here. So I said this was like our first one that we came across. Okay, there's 2 different ways you could do this. You could do this one like here. All right, you know what the kinetic energy is, then they tell you what the velocity is. Bet. Well, you can do this as a proportionality problem. Well, if V over here is 1/2 of what it originally is, if we make everyone a buddy a 1, the mass is 1, velocity is 1, the 1/2 is constant, so we don't even need it. They said, okay, we'll change V. It's 1/2 of what it used to be. Okay, well, instead of V being a 1, we make it a 1/2. You square that, multiply it by 1. It's 0.25 of the original KE. So this guy times 0.25 is going to give us 720. The other way you could have done it would have been, all right, solve for the mass. Mass would have been 2KE over V squared. And then once you solve for the mass, all right, you have the velocity over here. The mass is the same, it's the same rider. So M would be the same. And then you would just do 1/2 M, which we solve for over here on this side. You gotta solve for M. And then plug it into the 1/2 mv squared, and you would still get the same answer of the 1720. You would still get that same answer. All right, then the next one. You get this. Okay, I showed my guys, again, there's 2 ways you can do it. This way, I asked them to do the long way out. You have potential energy and you have the height. What we don't have is the mass. Rearrange the potential energy equation. All right, now you use 9.8 or you use 10. Okay, it depends on what you've used, what you've learned. I use 10 with my guys. So we kick out an answer of 50 kilograms. So that means we know what the mass is over here now. We see the height. Gravity is still our 10 meters per second squared, and solve for potential energy, and you get 2,000 joules. Another way you can do this real quickly is assuming the mass is the same, all right, for this guy here. All I did was take the total distance, or total height, and since it's now 1/3 of the original, if I did 1/3 of the original potential energy, I'm still going to kick out the same answer here of 2,000 joules. Then 3C, I believe we called it this one here. All right, you had potential energy, you know what the mass is, you know what gravity is, solve for the height. 17.5, so that means, all right, same picture, same building, we're assuming that it's the same height. So now you know height, the mass is this, and we know what gravity is, so you multiply them all out and you get this number here. A simpler way could have just been, well, if they're the same height, gravity doesn't change. The only thing that changes is the mass. It's double the mass, so the potential energy should be doubled since it's directly proportional there. And 875 times 2 is this 1750. And then the next one here, 3,700 joules with a mass of this. So you have kinetic energy, you have mass, solve for the velocity. By doing so, you work it out, you get 5 meters per second. All right, the vector length is the same, so we are assuming that it is the same velocity, and we know what this guy's mass is. So by doing so, we get a proportionality here of 850 joules. Or another version of that would be, remember that the KE is equal to the 1/2 mv squared. If we make it, those guys a 1 times 1 squared. We didn't change the velocity. We're assuming that it's the same, so that stays a 1. And we still square that, but it's not going to do anything. And over here, what we do? We got the mass, and we cut the mass in half. So basically, it's going to be 1/2 times 1, or so it's 1/2 of the original kinetic energy. And if the original kinetic energy was 3,700, you do 1/2 3,700, and it's going to kick out that answer. Okay, so with all of those, then it asks you, right, the clue from number 1 on the back, where it's like, oh, rank them all in rank the energies. So these guys here, right, are the answers, right? So you had 1750, you had 1850, you had 2000 and 1720. You rank them all in order from highest to lowest, and then you get these shapes that are on the back of the cards. Those shapes count up the number of sides, right? So this like has 4 sides, 3, 5, 6. So you put the code in a specific order, it would open up the next box, and you would then be able to go to section 4. In section 4, all right, you get another envelope that opens up with our new piece. All right, so there's 2 things in that. One is this looking thing. So this is the problem here. Now, if you're looking at this, you're like, okay, well, I don't have mass, I don't know what the velocity is, and I don't have kinetic energy here. So I can't find the total mechanical energy here at any point. So that's a problem. So what happens? Well, there is another piece of the clue in here. Inside, you get this. I saw this earlier in clue 1. So this is going to tell us, we're using a person who has a mass of 80. So now you know the mass. Okay, cool, that's great, that's helpful, but we still don't know what the height is. So even though we have mass and we know what gravity is, we don't have height, so we can't find the total potential here. Now, at the top, you're at rest, your velocity is 0, kinetic energy at the top is going to be 0. At the bottom, well, we know that the height is 0, so the potential energy would be 0 there. So we know at the opposite ends, you have 0 kinetic up top, you have 0 potential down bottom. So, but again, we're still missing a piece of information. We either needed the height or the velocity. Well, on the back of this code, or on the back of this, was the missing piece to the QVC code. And which, once you do that, it sends you to a link, and the link tells you that the velocity of the guy at the bottom is 4 meters per second. All right. So then this leads us here. We know that the mass is 80 and velocity is 4. Okay, so what you should have an idea of is that at the top, we're all potential, and at the bottom, we're all kinetic. So if you know what the velocity is down here and the mass, you can find out that the kinetic energy is this at the bottom. All right, and I wrote 640 at the bottom, height is 0, so potential energy is 0 at the bottom. So now that you know potential and kinetic at one position, you can determine the mechanical energy, the total mechanical energy. And it's those 2 pieces added together, which is 640. So that means at any point along that drop, at any one of those dots, the 2 things have to add up to be 640, no matter what. So now here they were like, okay, well, find kinetic energy. Well, 640, nope, that wouldn't work. That doesn't unlock the code. Right, it doesn't unlock the next thing. So what you should have done is then, if I need to know this guy here, I got to take the total energy minus the potential, and that will give me 425. So 425 plus 215 would equal the total energy, and bing, bang, boom, you are then open to the next stage. You are then in stage 5. Okay, the final stage, and this was a race as well. So everybody had to do the work, and everything is, along with it. Now for this one, let me see. Do I have this thing here? I do not. One sec. All right. So for this problem, this one's simpler than it should be, or than it seems. All right. You need the total energy from these two things because you know it. Potential and kinetic at one point. Add them together. 9.4. 9.4 minus 6. All right. That should give us what? 3.4. So that's potential energy. That's the answer to the first one. And on the second side of this, which is the other thing you needed, it's a roller coaster problem. I'm going to show you guys the setup for that real quick. Just give me 1 second. So with this setup, you get a problem with like a roller coaster. It's conservation of energy. Conservation of energy. The mechanical energy initially is going to equal the mechanical energy at the final point. Now, mechanical energy breaks down into the kinetic energy initial plus potential energy. So the equation was just, remember, we had just like this down here before. Mechanical energy is equal to kinetic plus potential, or potential plus kinetic, either way. So we're taking the mechanical energy, all right, at one point and the other. They have to be the same in an isolated system. And so we just broke it down. The initial velocity, the initial height, the final velocity, and the other height. So we didn't use these exact numbers because everyone had like a different card, but this is a similar, this is a problem. So you had a mass of 300. The height of the initial hill is 54 meters. The second hill was 40 meters. We don't know what that speed is. That's what we're trying to find. It says that the roller coaster guy starts at 0 meters per second. So that means your initial velocity is going to be 0. Wait, what happened? Well, why is the m gone? Well, the mass of the roller coaster cart and the people in it, or whatever, that doesn't change. So they are all basically able to be canceled out. So then the initial velocity at the top was 0. Gravity, all right, 10. The initial height, 54, equals 1/2 VF squared. We don't know what that is. We're looking for it. Gravity, 10. Second height, 40. Multiply at 0, 540. This stays same, 400. So you're left with this right now. All right, you're left with this. We want to get VF by itself. So you got to subtract 400 from both sides. You do, and you get 140 is now equal to 1/2 VF squared. To get rid of the half, you got to multiply both sides by 2, which gives us 280 is equal to VF squared. To get rid of the square, you got to square root both sides, and the square root of 280 comes out to be approximately 16.73 meters per second. So you will have a conservation of energy problem like this on your test. All right. So it goes through work, it goes through power, it goes through energy, kinetic potential, conservation of energy. So there's several different facets, very similar. All right, you're going to have very similar stuff from your quiz on there, and then you're going to have some of these problems. All right, so there we go. There's your breakout room test review.